Okay, so before we start, for the two things, right? I sent you an email on Tuesday. Only finished homework 1, homework 2 grading, and then I'm targeting on to finish another 2, maybe 3, hopefully by the end of this week or before next Wednesday. Hopefully before next Wednesday, and then we hopefully in another week we would be all in sync for all the greetings. And then that's number one. Number two, uh, for the for the discussions, I suggest you guys all participate, even though if I as I mentioned in the email, you don't really need to start a new thread or to to send some new view, etc. You can always just comment on other people's views so that I see the engagement from your end. You kind of following what people are thinking, some other fellow students are thinking of, etc. So that's that part. So if you haven't done anything before for the earlier weeks, please do so. It's really, I just consider that to be 3 points for you guys. And then for if you have any questions on the score, I mean the grade that you got for each individual homework, um, let me know. Send me an email so that we can discuss individually. So what I was trying to do is I give you a breakdown for each question so that you know which part you missed. Look at the answers. Look at the solutions from other fellow students, or try to look at it again. So ideally, we should have been doing this maybe 2 or 3 weeks later instead of already 7 weeks. I apologize for that. Just because the first 3 weeks we are kind of in the process of like 3 homeworks due, and then we almost like we started, and then we started the whole thing again. So we have, I'm trying to catch up with that front, and then um, you can take another look after you got the grade. I think that's probably one way that can help you with the learning process. So, any other questions in terms of on this front?
Harry,
Yep.
can you hear me?
Yes, go
Hello?
ahead.
Yeah, I was wondering, instead of getting fellow students' solution, is it possible to get the solution from the book's publishers? Because, I mean, the student solutions are good, but sometimes they can be wrong. Some of them can be wrong too.
Yes.
Because
Um,
since these questions are from the book, probably the solutions are available for instructors.
yes, they have solutions, but solution is really simple. For example, they give you a final number, right? And then you don't know how they got it. So I'm not sure if that's a good idea. I could do that. Let me take a look whether I can find that out. That's number one. Number two is I could try to find. I could actually. I have a version that I know it worked, so I can try to get some solutions myself too. And then you
Oh,
guys can, yeah, you guys
that
can
is,
look at that part, and then if you think it worked, if you have questions or if you have concerns, you think that some part is not really quite right, we can discuss as well.
okay.
Okay,
Thank you.
no problem. So any other questions on this front or other questions logistics wise?
Yeah, I was wondering if you could open a discussion thread so we can start forming groups for the project that you have listed on.
Yes, that's actually exactly the next thing that I'm kind of going to touch upon. I'm going to start a list, the roster. I know two or four of you already have decided to work together, so I'll just start from there, and then you guys can start putting together and uh, put more groups as you agree with each other, and then put more groups in there so that we know who is working with whom. And that's why I'm actually opening this syllabus. I want to see one. Oh, you didn't see it here. I want to see one is a due date for. Okay, so we should start doing that. Really start doing that this week. I'm going to initiate that discussion group so that you can start forming teams together. And then proposal is due by end of next week, which is a draft. This is like 10%, even though it's only 10%. And then final project proposal by 11th. With that being said, the whole idea is between this week and week 11, we can start talking. We will chat through email, through groups. If two of you are in a group, send me an email on this. Of course, the submission is actually, I believe it goes through the black box system. But we can initiate that process to talk to each other, and then we can finalize your proposal by end of week 11. And then you have a week, a month to work on the project. Yeah, the reason that we need more discussion is only because sometimes some students are a little bit too ambitious. The project scope is a little bit too big. Sometimes it's not enough material in the draft proposal. So that's the whole idea here for the first two some sort of deadlines there. Okay, any other questions? Okay, if not, let's continue with the week 7 material, which was last week. You can see my screen, right?
Yes.
Cool. So for week 7, just before we start week 7, remember that week 6, which is the chapter 7 of the book, discuss linear programming. I hope that you all were able to finish that simplex approach to solve linear programming. But the general idea is hopefully you would be able to do that once by hand, and then in the future you can start using solvers. Even though R has some LP solve, have some packages there which are listed on the week 7 material, I believe, in there. Even though it has that functionality, it's not sophisticated enough for some really big problems. So for smaller problems, it can solve, but for bigger problems, majority of the time you would use some sort of solver called a commercial solver called Cplex, CPLEX. That's one of the optimization solver. You can use C program or C++ program or Java program to call Cplex to solve optimization problems. That's most probably the most advanced commercial solver out on the market. There's some other ones, things like Lindo, Lindo, and on top of my head, there's another. It's called Ample, AMPL. That's another solver that actually can solve not only linear programs but all the optimization problems. So this is just some information for you so that in the future, in case you really need to solve complicated problems, you know where you should start. If it's really you need a scalable solution, you probably don't want to start with LP solve. It's probably okay to do a prototype, but it's not okay to run sophisticated big set problems such as traveler salesman problem. That problem itself is much more difficult to solve, which is an integer programming problem. I believe we're going to touch upon either, I couldn't remember, but yeah, it happened to be later in the section. I believe it's in the integer programming section. Okay, so let's continue. Let's continue with week 7 material. So we in week 7, we're trying to do one thing is how to model a graph as models, and then okay, Brian was asking whether those programs can be called from R. I think most probably not. Most probably not. Okay. And then in this section, we're trying to say that we are modeling how can we model using graph to model problems. And then we are going to start graphs as models, describing graphs, and then some of the graph models. And then we discuss how to use graph models to solve problems, and then the connection between math programming and um, and uh, math programming and also the graphs itself. Okay, so let's continue with the discussion. I'm going to respond to some of your comments there, chat or questions, etc. We can discuss a little bit more there as well after this section maybe. Um, so one of the problems that we had in graph is essentially we try to model. What we do we use, for example, in this road network, what we can do is we use some nodes to represent an intersection, and then use connections of the road to as edges on a graph. So with that being said, in graph there's some specific terminology that you should be familiar with. One of them, for example, it's node. Second one is the edge. So in this case, in this graph, we have A, B, C, D, which are the 4 nodes. Correspondingly, we have um, lowercase a, b, c, d, e, f, g as the edges, and then to represent the graph. And then as you can, and then if you think about it, what you can do is you can use the distance between A and C to represent the travel cost. You can use the flow on A and C to represent how heavily congested it is on A and C. I believe we already studied in IS605 as well, but that's some of the key points that we're going to cover. And then there's one very classic problem, which is graph coloring. Given a geographic map, is it possible to color it with 4 colors so that any 2 regions that share a common border of lengths greater than 0 are assigned different colors? So question is it possible? If we pick blue here, we cannot pick blue anymore in a different neighboring state. Is it possible? And then it turns out that it's possible, and then if we use different shape to represent a different color, that's a solution. You can see that it satisfies all the specific need that specific requirements that we just said there. None of them have, for the neighboring state, none of them have the exactly the same color. So, and then we said that in order to describe a graph, we need a vertex set, we need an edge set, and then we have some specific terminology. We say, okay, if an edge is connected to a specific vertex, we call it incident to the edges are incidents to this particular vertex. And then we have terminology of adjacent. Adjacent is something discussing between nodes. If a specific node is connected to another node, then we see that those 2 nodes are adjacent. And then number of degrees. For a specific node, how many edges are connected to this particular node, and then we call that as degree. With that being said, these are the key when we study social networks. This would be something that we are trying to cover. And then actually I want to show you something on the internet regarding social networks. This is basic information on the Wikipedia and on the social networks. I want to point out is there's some information that we get out of to understand social network itself from there, even though social network analysis itself is discipline itself, and it has more in-depth theory behind it. But based on this, hopefully we have a basic understanding of what it is. So if you think about this, and then if you look at this, what we can do is some of the major key elements of social network, including a couple of key things that would be centrality. Centrality refers to a group of metrics that aims to quantify the importance or influence of, in a variety of senses, of a particular node or group within a network. So if you want to, we can, and then in this way, centrality have between centrality, closeness centrality, and then alpha centrality and degree centrality, essentially based on a couple of measures, different sort of measures, to understand how central or important a particular node is. So even though we studied PageRank algorithm in IS609, 605 previous semester, but this is much more different angles to look at this problem. And then there are some other things. Density, the proportion of direct ties in a network relative to the total number of possible ties. Okay, and then suppose that one node is only connecting to the rest 3 other nodes, and then potentially you could be connected to all of the 100 nodes in the network. Then the density is only 3 over 100 for this particular. No, I didn't describe correctly, but in general, the proportion of the direct ties in the network, so we can count the number of direct links divided by total number of possible, which would be choose if we have 100 nodes, the total number of links would be choose 2 out of 100, which is a combination, so which would be 100 times 99 divided by 2. That would be the total number of total possible number of total number of links, right? And then we can use direct ties divided by this total number possible, so that we can get density of the graph. As you can, if you think about it, what you would get is, if you have a lot of links in the network, then it looks more crowded, and then the density would be higher too. And then, okay, continue with this. We have some other things like distance, structure, holes, or tie strengths. The reason I'm trying to point you to here is only because this can help you if you really want to continue with some sort of project on social network analysis. You should try to use some of this terminology as okay, and you say, okay, I generated 5 of these metrics, and then try to represent the network, try to understand which part is more important comparing to the rest of the network. How would that be important? Because how would that information inform us to answer some other questions? One would be, it can, for in the marketing perspective, you can just target on the important groups of people, right? That's number one. Another possibility would be in many of the early warning systems that we design, you want to, okay, we target the group of people that actually more important, they can spread the news to the rest of the group much faster than we would be targeting on those type of people, right? That's another perspective. And then in some other, even some other systems, such as even in the some of the I would say I couldn't remember, I couldn't recall the name of this word. But essentially, if you some sort of disease, if we know that this is a certain probability that this can be transmitted to some other people or some sort of thing, that way we can model that as a network too, and then we can measure what would be the influence of the or which group of people would be the influenced group by this some sort of disease in that case, in that aspect. So that's some example for you that how we can use how we can use graph models to understand the network relationship between people, between entity, between all kinds of entities, and how we can utilize that information using graph models, and how we can model those sort of problems using graph models and get sense out of the data itself. That's one thing. Let's continue with this. And then we switched gears here, trying to understand for some sort of data, how can we fit a piecewise linear function to the data. And then for this particular thing, we know that if we just connect all the dots together, it will be the best fit, which is the one in the middle, right? And then another possible fit would be the first one, and then could be another fit would be the third one, right? The first one looks like the error, relatively speaking, is probably too big, and then the third one is pretty well if we want to do a piecewise linear, and then the middle one apparently has overfitting problems, and then we don't know how to extrapolate beyond here. That's another problem there. So this point is to tell you that graph models can be, in some regard, visualization can help you to be part of the modeling process. And then there's some detailed discussion in the book regarding graph solution based on cost structure. And then, of course, we have other graph models, including minimum shortest path, including minimum spanning tree, including maximum flow problem. They are all classic integer programming problem. Even though at this stage we are not there yet, but later in the semester you would see, probably in week 10 or week 11, you would see the connection between graph models and integer programming there. Later in this section, we actually already started give you a flavor of that, which is just a start. And then from the softball example, it's a matching problem. If we think about one set on the left would be the people, and then set on the right would be the position a specific person, team member can assume, and then what would be the best set? What would be a feasible solution? It would definitely would have many feasible solutions. And then if we say, okay, even though R can be assuming rows both for position 2 and 8, he might be better on 2 than 8. So you can assign some sort of cost between R and 2 and 8, that edge. Assign some sort of cost on that edge, so that when you do the matching, you can find a better solution or optimal solution for your system. And then with that being said, some of this cost structure itself can be conditional on some other sections, right? R might maybe doing better on 2 if Ella is on 8, something like that. And then we can embed all those sort of information into that cost structure between the nodes, so that we could solve for the a better solution or optimal solution in this case, right? This is an example of using matching, and then as you can see, on the left and on the right, apparently you have distinct two sets of rows or two sets of entities that you want to model, and then they don't talk to each other between those sets. On the left, A doesn't have a connection to B, B doesn't have a connection to C, etc. Right? And then with the extension for this particular problem, another possibility what we can do is this graph can be directed. And then if A can assume 2 and 2, and then something like G can assume to 2 as well, we can have a variation of the graph being a directed graph, and then the solution would be different. I'm not saying this particular problem we need to do that. What I'm saying here is the modeling or trying to put some sort of mathematics or some sort of graphing models to a specific business problem that you are facing. The modeling part is really how you structure the problem. Start with from there, and then trying to continue with number one, whether that start is correct, whether that makes sense, and how can we what assumptions we have made, and whether those assumptions have significant impact on the model results. How can we further improve with better assumptions? If we can relax some of the assumptions better, how can we further improve? And what's the weakness of the model, etc. That's the whole thing. That's the whole pieces that you probably want to consider in the modeling process. So continue with another example here. So suppose that that policing a city example is a vertex covering problem. So that a specific node can cover a couple of cities, and with a certain cost or certain capacity in this case. And then the decision would be who should be covering which cities. Okay. Along this line, a question for Walmart would be which warehouse or which store should be covering which neighborhoods. Similar problem for Amazon too. Where should we set up the warehouse? And then the set covering or vertex covering problem, it's the same problem. Set covering and vertex covering problem is definitely being used by Amazon to make a decision on where they should put their warehouse. And then the book continues to discuss the Dijkstra's algorithm, shortest path algorithm, and also the maximum flow problem, meaning how can we get the maximum flow on a network. These networks problem can be used in many places, and used in different industries as well. Anything you can think of, social network analysis, transmission networks, communication networks, and then this distribution networks. So it can be used in many places in various forms. Can be really complicated problem, can be really, relatively speaking, can be simple problem. For example, in the airlines, how do you do the schedule? And then in the airlines, how do you do the crew pairing? Who should be working with whom on which schedule? That's the classic example for optimization. Also, even on train schedule, freight cars, freight trains, or passenger cars schedule, and even also one more example would be in a transportation network, you're trying to optimize the signal so that you can decrease the system delay overall. The system delays can minimize that number. That's another set of problem, which is a optimization problem, but they can be solved in some sort of graph models. And then the example has actually continued to discuss how to solve bipartite matching problem using maximum flows. By the way, the point that I'm trying to make is you guys should definitely read the book, and then we can discuss for some of the questions. It has a lot of detailed examples, and then hopefully that can give you some insights on later on in your real work. You realize, oh, I could formulate this business problem to some sort of math problem or graph problem so that we can, you can solve a real problem there, and then it's theoretically sound. And there are some off-the-shelf solution there. Okay. And then comes back to the traveling salesman problem. And then traveling salesman idea is from A. If we start with A, we want to travel all the cities, and then in order to make that tour, what's the minimized cost? And then in this particular example, the solution is from A to D to C to B, and then back to E and A. So the total cost would be adding the distance between all the points. And then the problem itself is, let me see if I think I do have the formulation here. Okay, I think so, yeah. It's not in my slides, but we can go that there shortly after those two slides finish, after the next two slides. And then let's look at this vertex cover problem. The idea is we're trying to minimize the cost so that every single, because the idea there was xi and xj represent a specific edge, right? No, ij represent an edge between all the edges, and then xi plus xj larger than or equal to 1, meaning that at least one of them, at least it would be covered by one of them. I think that's the formulation, even though, yeah, maybe it was worthwhile to do a quick search here. Okay, the idea here is cover every edge of the graph so that UV is the edge, and then as long as XU is covered, and then all XU plus XV larger than or equal to 1 essentially means both of them has to be 1. Because XU and XV can only take the value of 0 or 1. So in order to be larger than or equal to 1, so both of them have to be 1. And then once both of them is 1, meaning that the edge is covered. There's edge between U and V. Okay. And then here says every vertex is either covered in the vertex cover or not, and we're trying to minimize the cost. And then if for this particular solution, for this particular example here, we would be able to cover all the edges with minimized cost to cover all the edges by in this example, we only those 3 points, and then in the second example, you can use those 4 points. Okay, that's that. And then next question actually it is the on the notes I have the maximum flow problem. So the whole idea is to have the maximum flow on the network. And then with satisfying some of the capacity constraint. And then let's look at the formulation. So the formulation essentially is, one of the constraints is everything goes out to J, goes into J should be equal to everything goes out of J. This is called conservation of flow, meaning that we don't lost any of the traffic in the system, right? So anything goes into J would be equal to anything, the sum of all the flow goes out to J, goes out from J. That's number one constraint. Number two is the flow on edge between node I and J less than or equal to the capacity of that edge. That's the second constraint. And then the third constraint is the flow has to be larger than or equal to 0. And then what we're trying to minimize, or what we're trying to maximize is the flow between S, from S to J, or the flow to from S to J, starting point to J. So that's the math programming for the maximum flow problem. So the graph problem itself in the textbook, it tried to cover that, and then at the end we have this maximum flow mass formulation, so that we see the relationship between those two. And then last thing that I want to discuss here for this section is the traveler's salesman problem. So the idea here, if we look at the formulation, hopefully we have a formulation here, yes. So the decision variable is xij. The path goes from city I to j. Otherwise, it's 0. So that at the end, we would be able to connect all the dots together. We say, okay, I is connecting to j, j is connecting to k, k is connecting to l, and then we know, okay, how can we go from I to l and all the way back to I again. Okay, so that's that part. And then once xij is defined, cij times xij would be the traveling cost. And then xij has to be, so we're trying to minimize that travel cost as we mentioned here. And then the next thing is xij between 0 and 1. So it's actually either 0 or 1, right? But we use this variable because we want to avoid that binary problem. We want to formulate it as a linear problem. And then what we did here is, this is saying that from anything, I is the starting point, j is the ending point, and then from the starting point, you just go to one of the j's. All the options, you only go to one of them, right? At the end, you can only coming from one of the nodes from outside, coming back to I. So that's the idea. for those two constraints. And then the last constraint is actually called subtool, avoiding subtool, meaning that you don't want to your solution would not be finishing this part again and then continue with some other things. That's another possibility for this particular solution. That's why the last constraint is called uh, avoiding subtools. It's relatively more harder to explain, but that's a general idea. And then because of this constraint, the last constraint, the problem is much harder to solve. Without the last constraint, it's actually straightforward linear program problem. It's not hard to solve, but really the last constraint that actually makes the problem much more complicated. And then here is a little bit more detailed discussion on how this is actually formulated here. Hope you can, if you could read it when you get a chance, and then that will be something useful to know. Okay, let's continue with the second section here. This part is probably relatively short. Let's see. Hopefully, yep. So this part is the how to modeling with decision theory, and decision theory itself is another branch of math modeling. And then decision tree is probably something that you heard of, and then sequential decision and conditional probabilities, and then also at the end the problem actually presented the decision on the alternative criteria. This is some sort of, in many of the project management courses, this you probably have already studied this, or you have probably studied this in the economics course, some of the macroeconomics course as well. If not, let's take a quick look. In general, it's straightforward. And then it has, as we mentioned earlier, from modeling perspective, it can be deterministic, it can be chance or risk. Once it's chance or risk that involves chance or risk, then it's called stochastic modeling. And then for chance and risk, we do have probability and expected value, weighted average, and also we can do sensitivity analysis. I remember that someone in the class was trying to ask this question, why this is expected value. I think it actually makes sense, because if you have n possibilities, and then p1 is representing the probability for the event 1 happening, and then a1 is the w1 is the corresponding payoff. Then w1 times p1 is actually payoff that we could obtain for outcome a1, and then add all of them up, that will be expected value of the game. So that makes sense, right? If you still don't quite understand this, we can further discuss this. Also, you can discuss with some of your fellow classmate as well. Continue with this. In a decision tree, so two types of nodes. One type is called decision node. One type is called I couldn't remember that. One type is called decision node. The other type is called probability node, actually, right? So, okay, that's correct. Yes, it's probability node, and then I believe this is really the probability node. So the circle one is a probability node. So we have a probability if we have a new construction or we remodel. And then for the new construction, we have two probabilities. One is successful, the other one unsuccessful. And then what would be expected value for new construction. And then correspondingly, we have an expected value for remodel. And then based on remodel and new construction, we could get a decision. We can decide on the expected value on each single pass, and then decide on which one would be the best alternative, right? And then, as you can see, it's most probably it's no longer it's no longer it's highly possible it's not only two alternatives. It could be three, it could be five in any of the nodes, and then at the end, expected value would be different. I mean, you have different branches on the tree. And then it comes to this sequential decision and conditional probabilities. And then you could make a decision on multiple stage. And then this actually leads you to game theory, which would be next section, I believe. I mean, next chapter, I believe. We can go through more detail. If not next chapter, will be the chapter after. And then same thing, just for as being how this can be used. It can be used in the example that we discussed, new construction versus remodel, or you could think about how some of the investment strategies. How can we implement different strategies on different scenario? That's the decision using alternative criteria. And then this is the homework, and you can finish homework in chapter 9. Okay, that's it for week 8, and then let's go through some of your comments here. Let's see if I can maximize this. So let's see if you guys have some discussion here. Okay, so earlier someone was saying that there's RCPP package that you can call RCplex, yes. Probably so that, but I'm not sure how sophisticated the model, I mean the RCplex itself is. I have never used it. Hopefully it's most probably can be sophisticated. Probably for large scale problems it has difficulty to solve because of the memory issues, etc. But for others it can be a good solution. RCplex. And also RCPP can be used to call compile C program. That's true. Thanks a lot for that comment. And then continue. Lindo seems to have an API that we might be able to use from Python. That's probably true as well. Even though Lindo is, I think it's free. The more complex version is called Lingo. Lingo, I believe. Yeah. Yes, earlier I want to say that epidemiology in that study you can see how quickly what's the affected group that we can focus on that group if the network is constructed reasonably well. And then Bytonic 2. Okay, was almost exactly what I needed. Okay. This is something that I never heard of, so let's see. So this is almost similar to traveler's salesman problem. I don't see what's the difference there. Ah. Set point size in a usually is closed polygon chain.
Hi, this is Daniel. Can you hear me?
Yes, go ahead and explain.
Yeah, basically the problem I needed to solve is I needed to be able to do a perimeter route. So it wasn't the shortest route between the points, but exclusively a perimeter in concept, the shortest route, but not by crossing through. And so this Bytonic Tor basically achieved that. I think it did what it was advertised that it would do. It did achieve the shortest perimeter route. It came up with some interesting choices that weren't exactly what I needed, but for the most part, it really solved the problem for me. So the perimeter aspect of it was the key point that for me it differentiated from the traveling salesman problem in general.
I see. And then itself is solved optimally, or it's a heuristic to solve the problem?
I understood it to be a heuristic. I ended up, if you scroll to the bottom, there's a Canadian airline problem paper by Guerrero. I ended up using that. He has the algorithm in that PDF, and I ended up basically coding it based on his. He has some pseudocode in there, and I ended up taking that pseudocode and coding it into a C# program for my use.
That's nice. And then, if you don't mind, what's the usage for the algorithm for any business problems, or no?
Sure. Basically, the data I have is GPS coordinates for a signal from a satellite, and we were trying to detect the boundary of the satellites and compare it actually to our service provider's advertised boundary for their satellite beam. So I took a center point within the region and measured the maximum distance in the 360 degrees around the center point, and then wanted to connect all of those dots around the 360 degrees to create a concept of what the boundary of the satellite coverage was, so that we could then compare it to their advertised map of coverage.
Okay, interesting. Yep, thank you. Thanks a lot for sharing that story there.
Sure.
Yeah, that's exactly one of the reasons we have this course would be you have exposure to all these sort of possible solutions, and then maybe one day when you start facing some sort of business problem, you can use you would have the capability to search to find out what would be the best that fits your need. And then that's great. Oh, okay. So that's the reason. Yeah, it should be W1 times P1 plus W2 times P2. I probably missed that part. So it should be different W's there.
Okay, yeah, that makes sense. That's what I thought, but I wanted to make sure I wasn't missing something also.
Yeah, great. Thanks a lot. Didn't get how the decision tree is being calculated in the last page. Okay, let's discuss that. Okay, thanks for sharing from Daniel. And then we can answer the last question that Nandi has on the decision tree, right? So for this particular problem, because it's a sequential decision, right? It's a conditional probability. So let's say, I believe the expected value, right? Expected value of spin 1 is depending on the expected value of spin 3. Let's say if my conjecture is correct. Let's look at whether spin 3 what's the spin 3 value? Spin 3 value would be 10 times 0.25. That's 2.5 plus 6 times 2.5 is 1.5, so that comes to 4. And then this would be 1, this would be 0. So expected value for spin 3 would be 5. But the expected value for spin 2 is dependent on the expected value of spin 3. So or should we go in from the beginning? Let me think about it. Yeah, we should be. I think we should be looking. I don't know. Let me think about it. Yes, that's correct. I believe so. Yeah, if we continue with this, right? We continue with this logic. We come back to this node. That meaning that we can back out what's the expected value for spin 2 as well. Correspondingly, for different paths, we can get the expected value for spin 1, and then for spin 1, how did we get this value, and then we can traverse back to make a decision on which we should be taking, which route we should be taking. I think that's the general idea there, even though I'm not 100% sure. Actually, we probably should do something. I should take another look over there on that too. We can discuss a little bit more offline in email or something. But actually, this actually reminds me another question that we had last time. We were trying to discuss the convex. What is the definition of convex? So I want to draw you here. The convex idea is any of the if you connect two of the points in the convex hull, anything in between should still be in the curve, in the convex hull. So if we connect 2 points, A here and B here, any points in between still lies in this convex set. That's called convex. So we can do anything there, but for concave function or concave curve, we know that if we connect 2 points, one of this, one of that, not every single point will be end up in the curve itself, right? Some of these curves in here is no longer, some of the curves in here is no longer in the set. That's why that's the definition of the convex there. Yeah, I can look at this problem again and we can discuss more. And then we can continue discussion. So for the not finding solution, how the second node and first node. Let's do a little bit more calculation here. Okay, maybe we can get that. Okay, this is a decision node, right? So at this stage, you have a decision to make. You can take that $6. What's $6? Where is this $6 from? Okay, for the second spin, you have a couple of possibilities. One of the possibilities is this. You can take that $6 or you go to spin 3. So second spin, let's get this value. This is 10 times 2.85. That's 2.5. That's straightforward. This one is straightforward to calculate as well. That's 1.25. So that's 2.5, 3.75 already, right? And then the next question is how we can get this. So it would be 6 times 0.25, that's 1.5. And then this would be 4 times 0.25. It's not 6.5. There's something else, this conditional probability here. Yeah, let me look into this problem and then we can discuss more. Of course, maybe I'll send you an email so that everyone is I can use this model for my project. For label propagation. Yeah. Okay. Yeah. Let me look into this. I'll send you guys an email so that it's better explained, and then we can understand a little bit more. Okay. So you have any other questions here on anything? Okay. If you don't have any other questions, then we can stop here. And then, as I promised, I'll try to catch up with the homeworks. Hopefully 3 by next Wednesday, and then another 2 or 3 by the week after when we talk again next time. Okay. Good night, everybody. Yeah, Burton, it is still 3 problems. Yes, that's the same policy for the whole thing. I'm not sure if you're still here.